So there are several concepts we've just discussed about two-dimensional vectors that we need to be aware of and will utilize throughout the rest of the semester. Continuing on, there are some concepts about three-dimensional vectors that we need to discuss. The first one is what we call coordinate direction angles. Now I'm aware this may be the first time you've really worked with three-dimension objects or drawings or anything of that nature, and that's okay. We do dive headfirst into it. The math is about the same, it just gets one more dimension complex. We've mentioned before, typically I like to draw my y direction left to right being positive y. The x direction represents what's coming in and out of the page at you, right? In and out of the page, that's x. But I can't draw it that way, I have to draw it off at an angle. And that leaves then drawing z up and down in this vertical direction. And if we do that, and it really doesn't matter, you do have to follow what's called right-hand rule. That is, to go from x to y. If I close my fingers with my right hand, closing my fingers from x to y, my thumb will point in the direction of z. So you can see here, if I go from x to y, my thumb is pointing on my right hand, my thumb is pointing in the z direction. If you're left-handed like me, you have an advantage here. There's very few times as a lefty we have an advantage. This is one time where I can be writing, I'd be like, oh, which way? Oh, yep, that makes sense. That's Z. If you're right-handed, you'll actually have to put down your writing utensil to do this. But that's what we call right-hand rule. To go from X to Y, your thumb will point in the direction of Z. So as long as you draw, I could draw X out here and Y back there. As long as I draw Z, X, Y, and Z, that's okay. That is technically correct. This is the way I would normally draw it, though, right? You'll see in the book they'll use all kinds of weird angle systems, but I digress. Let's continue on. Let's say I've got some random vector A coming off the origin out here. Some vector A. A way we can describe this vector is by the angles formed by the positive axes out to this vector. And so the angle measured from the positive x-axis to vector A, we would call that the alpha angle. The angle measured from y to the A vector is the beta angle. Have some way of drawing your beta different than you do B. I keep mine pretty simple. It looks a lot like a B and I just put a little tail on it. But have some way of drawing by hand a beta that looks different. And then gamma, my gamma typically looks like an alpha. I just rotate it 90 degrees. The gamma angle is measured from the z-axis, the positive z-axis. And what you can do is you can say, well, the components of this vector, right? If I take how far it goes out on the x-axis and how far it goes out on the y-axis, that we'll call it AY, and it goes up a certain distance AZ on the z-axis. Right? The lengths of those, the magnitude of vector A, we could find with Pythagorean theorem. That'd be the length of A in the x direction squared plus the length of the vector A in the y direction squared plus the length of the vector in the z direction squared. If I square all these terms, add them together, and take the square root of that sum, that gives me the length of vector A, the magnitude of vector A. And then I can find these angles by a cosine. I can say that the cosine of the alpha angle is going to be the length in the x direction, AX, divided by this magnitude, which again, this is a technical way of writing the magnitude, but if I just write A without a hat on it, that also means that's the magnitude, the overall magnitude of A. We've discussed that briefly before. I can also find cosine of the beta angle as AY divided by A, and then finally the cosine of the gamma, I'm sorry, let me just draw it over here. Cosine of the gamma angle, if you have room, just draw it to the right. I messed up and I don't have room to the right. That would be AZ over A. So using the cosine, I can find any of those angles, and there's a neat thing, kind of one more equation if I'm trying to find these angles, or you just need an additional expression. Cosine alpha squared plus cosine beta squared plus cosine gamma squared, that sum will give you 1. So, just an additional relationship relating those quantities together. I'll be honest with you, we'll use these angles a little bit in Chapter 2, and it'll be very rare in our course that we'll use them after that. They're valid, they work. We just don't typically use them very often. But let's work through a quick example with one, or a couple of them actually. Let's work through an example here. So I've got standard X, Y, and Z axes there. And if I draw a vector up here, similar to how I drew my A vector just a little bit ago, and this is 875 pounds. And then I've got another vector going kind of pointed down. We'll say this one is 1,000 pounds. Now, we're going to describe these using these alpha, beta, and gamma angles. So this first vector here, I'll draw a single line on these angles from the x-axis, the y-axis, and the z-axis. We'll just draw a single line arc on those. So this is 60 degrees from the x-axis, 50 degrees from the y-axis, and this ends up being the remainder based on this expression here of about 54.5 degrees from the z-axis to that 875 pound force. Now let's use double arcs to describe this other one to kind of differentiate them, make them easy to tell which one's which. The alpha on this one is about 52.5 degrees, same as the y, so it's kind of right in between the x and the y, 52.5. And one might say, Steve, if it's halfway in between, wouldn't it be 45? Well, it would be if gamma was 90 degrees, but gamma is not 90 degrees. This thing's actually below the xy plane because gamma here is 120 degrees. So it's actually down below. The xy axis would be up here, and this vector is pointing down below that. It's 120 degrees below. So that's the reason these are not 45s. It's further down. So to get down to it, these angles have to be a little bit larger. And I've not really drawn it that well for you to see that. It's hard to draw 2 dimensions on, or draw 3 dimensions on a 2-dimensional media. The best you can do is project it, you give a representation. Sorry, I know I clear my throat a lot. What are we doing here? Find the resultant, which is just to say add these 2 vectors together. Cool. Well, as we discussed before, the resultant is simply going to be the resultant in the x plus the resultant in the y, and I'm multiplying by these unit vectors here, I, j, and k, plus the resultant in the z times the k vector. Now, I can find the resultant in the x by adding up the x components here. All right, so the x component, notice I've got these expressions earlier. The x component would be, if I take the cosine of this angle and multiply by the length, that's going to give me the x component. Well, I know the length of the magnitude of each of these forces, 875 and 1,000. I know the alpha, beta, and gamma angles. So the unknowns here are the x, y, and z components of each force. So for the 875, if I take the 875 pounds times the cosine of this 60 degrees, that'll give me the x component of this you can't see that, I'm sorry. 875 pounds, and if I take the cosine of this 60 degree angle, that's going to give me the x component of this 875 pound force. And if I add to that the x component of the 1,000 pound force, right? Well, it's going to be its magnitude, 1,000 pounds. And then I'm going to multiply it by the alpha angle, this 52 well, it's cosine of the 52.5 degree angle. And again, I'm using this, finding the x component based on multiplying the length by the cosine of alpha. And then I can also do the same thing then for the y direction. I can take 875 pounds, that's this magnitude here, times the beta angle, the cosine of the beta angle, cosine of 50 degrees. Add to it we're going to find the y component of this 1,000 pound force. So I'm going to take the 1,000 pound magnitude and multiply by the cosine of this beta angle, cosine 52.5 degrees. And then finally, to find the z component, RZ, I'm going to add all the z forces. Well, I've got the 875 pound force multiplied by the cosine of 54.5 degrees. I'll get better at that. And then add to it the 1,000 pound. And here I'm going to take the cosine of 120 degrees. Now, one might say, Steve, isn't this in the negative z direction? Isn't it down? Why wouldn't you subtract it? You could subtract it, but what you would want to do is you wouldn't want to do the cosine of 120. If you subtract it, you want to do the cosine of 30 because it's 90 degrees to the xy plane, and then it's another 30 degrees below the xy plane because it's 120 from z here. So if you want to say, well, it's in the minus z direction, that's fine. Just use 30 degrees here, and then you could throw a negative sign. But if you take the cosine of 120, you're going to get a negative, I think, negative half, right? So you don't want to have a negative and then take the cosine of 120. You either want to have minus cosine 30 or you want to have plus cosine 120. All right, I'm going to let you run these through your calculator. I want you to pause here, run these through your calculator, and let's see what you get. Okay, you got something? Awesome. So R, the resultant vector, I'm just going to give it an x, y, z components. That's going to be 1,046 in the I direction plus 1,171 in the j direction plus 8.1 is all in the k direction. And these are all pounds. So you could write pounds after each one of these, or since they're all multiplied by pounds, you can just factor that out. We could find the magnitude of this based on this and this expression up here. Right, go in that expression right there. And then once we know the length, we could take the x, y, and z components and backtrack using inverse cosines and find the alpha, beta, and gamma angles. If you want to describe this as magnitude and alpha, beta, gamma angles for the resultant. If the problem didn't specify, and this one did not, it just says find the resultant. This, a lot later on throughout the course, the x, y, z components are going to be more practical. Okay. I think I'm going to stop there. It's a nice stopping place, and we'll talk about position vectors.